Alrighty, so hello and welcome. Howdy. Here we are. Another problem today. I'm really feeling quite good about myself having solved the other problem from yesterday. Let's see, is the camera in a good spot? Just kind of, yeah, looks okay. I mean, maybe we could do a little bit higher, just a little bit. Maybe just a little higher. There we go. So, guten Morgen. Guten Morgen. Hallo. Hallo. Alright. The problem we're working on today is the next one. Man, I feel so good. I feel so good having solved the problem. Oh yeah, let me lower the volume a bit so it's not so loud. I feel so good having solved the problem yesterday. But on to the next one. On to the next one. So, candy. Let's take a look. Haven't looked at it yet. Also want to okay. So our goal is to go through all 2,000 problems on this website. Let's do it. There are n children standing in a line. Each child is assigned a rating value given in the integer array ratings. Also, one more thing to check. Okay. This is very likely going to be a DP solution. Oh, not that one. You are giving candies to these children subjected to the following requirements. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. Return the minimum number of candies you need to have to distribute the candies to the children. Okay. Ratings 1, 0, 2. 5 you allocate to the first, second, and third child with 2, 1, 2 candies respectively. I think I've seen a question like this before. 2 times 10 to the fourth. So 20,000 ratings between 20,000, 1 in 0 and 20,000, 1 in 20,000. Excuse me. All right, let's see. I'm going to use a vector. All right. N children standing in a line. Each child is assigned a rating value given in the integer array ratings. You're giving candies to these children subject to the following requirements. Each child must have at least one candy. Children with a higher rating get more candies than their neighbors. Minimum number of candies you need to distribute the candies to the children. So, okay. Interesting. So, I mean, I think this is quite literally like the higher rating just needs to have more than their neighbors, doesn't need to have more than everybody. I was going to say, if it was everybody, so I got to think about this for some time. Not obvious how to solve this one. Probably some kind of a DP solution, but maybe not. I don't know. 20,000 is probably not good enough to do quadratic time DP. So maybe this needs to be linear n log or n log n. Excuse me. Oh, I'm very tired. I think one issue, right? So if it was just more than everybody, then you can do a you could do like basically add 1 to every value, and you'd be done. Or do that in linear time. That works, but that's not the minimum. There might be something better than that, smaller. So what you need is just every locally for a position compared to its neighbor. It needs to be less than the neighbor. So I think it's as simple as just you could just go left to right, or not just no, well, not that simple. But one idea is anywhere you see a number that that is 0, you add a candy there, and then the neighbor if your neighbors have a higher rating as well as at any position than the neighbors, you'd have to add a candy there as well. So 201, 2 has a higher rating. Excuse me. And so that needs to have at least one candy as well. So I guess we could initialize our array with one candy to everybody. And then 2 is greater than 0. You add 1 to 2. When you look at 0, you have 1, and that's fine. The element to the right has 1, so 0 should be less than that, right? 2, 0, 1, so you'd add 1 on the right side. So you could do 2, 1, 2, and that gives you it's just local. Like you don't care about comparing the elements to each other. You only care about comparing the elements locally. The only issue is that local changes can become larger changes because they can cascade. So when you look at the second element and you say, okay, the 2 on the left have to be larger, they can be the same amount. It just needs to be larger than whatever's there. Then you look at 1 and the left side 0, now you have 2, 1, 2. So I think that works. You do 5 for 2, 0, 1. Yeah, okay, that makes sense. Or 1, 0, 2. So 1, 2, 2, let's take a think about that for a moment. So 1, 2, 2 could be, this is a good example where we would want 3 to 4 numbers and random values for each one. So we can say 1, 2, 2. Can we have the same amount if they have the same ratings? So if it's 1, 2, 2, we can also do 1. It has to be 1, 1, 1, and the second has to have 2. So that's 4. And I think that's what they're explaining, is that if you have the same rating, you don't need to perform this check. So it's only if it's greater than do we need to add numbers. Right? If there's a difference. If they're equal, we don't really care. You can allocate to the first one, third, and third child. First, second, third with 1, 2, 1 candies respectively. Third child gets 1 because it satisfies the above 2 conditions, which is must have at least 1 candy. Children with a higher rating get more than their neighbors. Okay. So, what if you had like 1, 2, 3, 4 or 1, 2, 2, 2? I guess you could just compare. I mean, can you do just a simple one pass left to right? I don't know if you had like 1, 2, 2, 3, 4, or 1, 2, 3, 4, right? So 1, 2, 3, 4, you do 1 candy for 1, and then you would look at 1 compared to 2. 2 is larger. This seems like similar to like a sorting algorithm type of thing, but instead of modifying the position, yeah, it seems very similar to like a sorting algorithm type of thing, where instead of modifying the position based off of its value, you're going to modify the amount based off the value. But it's going to be relative. It's not going to be in comparison to the other values necessarily, although you do have these kind of chains where, like a monotonically increasing sequence 1, 2, 3, 4, you would have to increase, right? You'd have to say, so you have 1 is incremented to 1, 2 would have to be larger than the 1 on the left side, so it would go to 2. 3 has to be larger than the 2 on the left, so that goes to 3. 4 has to be larger than the 3, that goes to 4. So you just add, I guess what you would do is say, take the, if this is larger than the value to the left, then increase to a number greater than the value to the left if it's large. So take the value to the left, and you could take the, if we're going left to right. So here's the deal: if we initialize with all ones, if we go left to right, we don't actually need to consider the value on the right, because we would say the maximum of the left and right values, but the right value is always going to be 1, so the maximum on the left is always going to be larger than that, so it doesn't really matter. You could always just take the one on the left. And that's pretty much it. And that's a simple way of doing it, is just say whatever is to the left, if this is greater, then take whatever's on the left, add 1 to it, and make this one that. So now if you had like 1, 2, 3, 4, you'd end up with 1, 2, 3, and 4, and add all that together, which gives you 10 total. But like, what if you had like 1, 2, 1, 4, right? So 1, 2 is larger than 1, goes to 2, 1 is smaller, we could leave it at 1, 4 is larger than 1, we can go to 2, so we go 1, 2, 1, 2. I think that works. Is there a situation where this doesn't work? Or is this not correct? Let me try that. I think it's that simple. So we're just going to say vector v, and we actually can do an int vector v of size r. We'll call them, instead of ratings, we'll call them r dot size for int I equals 0, I is less than r, dot size plus I. You can also just say int n is r dot size. Save a little bit of typing here. Say v of I is equal to 1. And we're going to say for int I equals 0, less than n, plus I. We're going to say if, so we'll say const int, it's also const, previous, it's going to be v of I minus 1, and we'll say if previous is less than, so we can say PR and PV, PR is R and PV is V. Is this really a hard problem? I mean, I probably have the wrong algorithm. So if previous rating is less than the current rating, which is R of I, then we're going to set V of I to the previous value plus 1, and we're also going to take our total. I have to prove that this is correct though, somehow. Ret plus equals PV plus 1. And that's it. This is what I've gathered so far. I don't know if this is right though. TLE. No kidding. What? What? Oh, minus 1. We got equal signs where there should be addition, there should be subtraction signs. That's kind of funny. Why is it TLE? I wasn't expecting that at all. I'm blind, man, I'm blind. Oh, okay. I'll put 2. This starts off at n. I missed that also. It's taking a long time. Okay, let's put some other test cases in here. 1, 2, 3, 4. 100, 5, 20, 21, 22, 6, 3, 7. Let's try some random numbers. and then 0, 10. How many ratings? Yeah, there's at least one, and the values could be a lot of different things. So we could generate some random test cases, I suppose. Wrong answer. Okay. That's interesting. 13, 19, 13. Supposed to be 10, 17, 10. Okay. So 1, 2, 3, 4 should be correct. 1, 2, 3, 4. So I must have misprogrammed this. That was actually one of the use cases we were just describing. Okay. Oh, we don't add 1 because we already added that 1. I mean, that's my mistake. Yeah, that's my mistake. Whoops. Slight error there. But still, it shouldn't be that easy. Yeah, I think this is. Huh. I think actually this. Yes. Well. Okay. Still misprogrammed. This is pretty subtle. How are we doing on time? 17 minutes. I wouldn't say it's super subtle, but it's. I don't know. I'm doing something wrong here. So. We want to add. So really, this should start out. We could do it this way. We could do 1, and then PV plus 1. No. Okay. How many? All right. Let's do n. So v is going to be set to PV plus 1, and from 1, and so the difference. So we added PV values. But how do we get 4 instead of 5? It starts off at 3. We say 1 is 1. Okay, fine. 0 is smaller than 1. Oh. So that's kind of an issue too, huh? Oh yeah, we don't really do anything about that if we drop down. So we figured out what happens if we go up, but we didn't really figure out what happens if we go down. So if we go down, well, I guess we could remove candies, but we would add one to the one on the left. Let's think about that for a moment. Actually, we can handle that too, because the thing on the right, in the worst case, it can only be, it would just be a 1. So the only scenario we have an issue is where if our current value isn't at least 2, then we have a problem. So we can say and we can say else if now if the ratings are equal to each other, we don't need to actually do anything there. Excuse me. It doesn't matter if one is larger than the other. We only care if the higher rating gets more candies. If they have equal rating, it doesn't matter which one way or the other. Yeah, so we could say if PR is greater than R of I, right, then we just have to make sure V of I, so we would say V of I minus 1 is then equal to the maximum of itself, which is PV, and 2, and then we would add the difference between V of I minus 1 and so you could say int new val is equal to standard max of PV and 2. Say V of I equals new val. And we're going to add the difference between the new value and P of E. How many we added in that scenario. Okay. Yeah, which should only happen, yeah, okay. Basically we add or subtract 1 there, more or less. That's pretty much the only case. It's pretty much this is just add 1, really. This could just be plus equals 1 and set this to 2. PV has to be less than 2. For this to even happen. If the rating is higher and there's only the candy on the right, there's only going to be 1. The rating is higher, there's only candy 1 on the right. The only problem you can run into is this just needs to be at least 2. So really you would just say if it's higher and you could do this too, and PV is less than 2, then you just add 1. It's kind of the same idea, same thing. How are we doing on time? 23 minutes? Okay. So let's try some of these other test cases. Now, I could be wrong about this. We might not need to, like, this could be the wrong idea. Maybe there's more that needs to be done here. Maybe I'm missing something. Very likely I'm missing something. Oh, okay. Looks correct so far. Let's try some other test cases. I think that's it. 20,000. Yeah, it's never empty, right? There's always at least 1. I don't know. We can do our what do they call that? Oops. Kind of want like a bunch of random tests, but we can do our generating test cases. It's a program I want to write to be able to kind of just quickly generate these test cases. That way I can easily test my programs. But let's do tempi. Okay. Oh wow. Let's put that into. Okay. Probably would be correct if I get these ones right. Wrong answer. Oof. Oof. I actually was expecting it to be correct. There are a few here that are wrong. Wow. All right. All right, let's try the last one, all the way at the bottom. All the way at the bottom. Let's do it this way. Copy, paste, and we'll take the one all the way at the bottom. Okay, so 6, 5, 4, 3, 2, 1. Oh, that's interesting. So we handled monotonically increasing, but we didn't handle monotonically decreasing. So the problem with incrementing one of these on the left side is that that could affect, oh, I see the problem. Because if we have 5 and then we say, okay, we need to increment to this to a 2, the problem is that if we increment this one to a 2, then the one on the left is that condition breaks. So this has to be monotonically decreasing. So we can break this up into monotonically increasing and monotonically decreasing sequences, and say for the monotonically decreasing sequences, you need to have and it's got to be strictly decreasing or strictly increasing, right? You can say basically it'll be the reverse of the increasing. So the increasing left to right, basically, however the length of the sequence is, you'd add a candy going all the way up. So you would say, and I guess there's a couple of considerations. Do we just want to calculate, like, do we just want to start off a base of 1 and then just take the sequence and say, you know, pretty much that's a, it's like a summation from 1 to n, something like that, where n, or 1 to x, where x is the length of the monotonically increasing sequence. I mean, yeah, that's fine. If you did it that way, you could do that for every sequence. That's not really a big deal. I mean, I guess one problem with that though is the sequences that are decreasing, monotonically decreasing, it's the same deal, but the problem is you could have a decreasing sequence and then the next value increases, so they're sort of a decreasing sequence into an increasing sequence, right? And the problem with that is that next value. Yeah, you probably, it's probably better to, I guess what I want to say is that the sequences are not disjoint. They actually connect potentially one to another, which makes things a little bit challenging. I guess what you want to do then is take the next value and figure out, so we want to split this up into increasing and decreasing sequences. Take a look at, so you always have a starting point. Look at the next value, next rating. If it's larger, then we have an increasing sequence, and the size starts off immediately at 2. So our size could initialize at 1. If we, I'm wondering if I should have an internal loop to take care of the sequence. That might be easier to think about, to do that logically, instead of trying to break this up into, yeah, I think that's easier. So we can say we have a outer loop and 2 internal loops. One internal loop checks for increasing sequence, the next loop checks for a decreasing sequence. Either of them could occur in any order, doesn't really matter. Maybe we'll just use a while loop then, and the index that we're at once the next check occurs will always be the beginning of the sequence. And could use for loops. I think that's fine. Just thinking here. We don't need to process the last value in the array because we're always going to be looking at pairs I and I plus 1. So last value of the array we could just leave. We don't need to process that one, I suppose. Yeah. Okay, interesting. Just pondering here. I think I have an idea. Have an idea of how this could be done. Have an idea. Ich habe eine Idee. So we'll do it this way. I starts off at 1. We're not going to increment I here is less than n minus 1. And we're going to have 2 internal loops. Identify monotonically increasing sequence. And then decreasing sequence. Okay. And we'll start at I, so we'll do int x equals, or we could say have an int count equals 1, or yeah, let's do x equals I. X is less than n minus 1, and r of x minus 1 is less than r of x. And we're going to keep incrementing x. Basically have duplicated code here. Set x back to 1. And this is, or back to I. And this is increasing sequence. So the monotonically increasing sequence, we say ret plus equals, we actually don't need a v, by the way. I don't think so. We could just start right off at n. Ret plus equals, it's going to be this value, or we could say, yeah, constant L or I, J, X, Y, Z. What the length? The length is going to be x minus I plus 1, right? Plus equals the length times length plus 1 divided by 2. And actually we're going to subtract 1 from the length, so subtract 1. How the calculation works, we just subtract 1. And then we're not going to make that a constant, we're going to reuse this variable. And then over here we do the same deal. Length is going to be x minus I. Ret plus equals length times. Something like this ought to do the trick. Now the question, no, not entirely, not completely. Part of the problem is that we would end up getting stuck at now you update I equal to x, and then now x goes back to I again. Traverse past sequence. Okay. Now there's a couple issues here. One, the calculations could be off slightly, sort of off by one error, and then also another issue is specifically what if these are not monotonically increasing or decreasing sequences? Excuse me. Then you would just traverse past. Non-changing sequences be ignored. So a non-changing sequence would be if they're equal. And this time it's I. If they're equal to each other, we don't need to do anything. We just leave it, I believe. Something like this. Let's see if this works at all. See if it compiles. Let's start with that. There's probably a bunch of errors in here. TLEs. Okay, so why is it TLE? Well, this should decrement here. I equals x. Oh, I think the reason is because we don't process over here. No, we could print I and x. Just debug. Just see what's happening, get a better sense. It's not too obvious what's going on here. I could maybe break this up into like separate routines or something, but I don't think we need to go that far. Just so that way it's like I can code it faster, kind of a deal. Approaching 40 minutes, so this is kind of a lot of time that we spent here. So I, and then x is x. I think we don't need that quite yet. Okay. Yeah, this is not the best way to code this, in my opinion. It's a little bit wonky. It's a little awkward. I is 1. So that's a little weird. X is I, which starts off at 1. X is less than n minus 1. N is, in this case, is 1, 2, 3, 4, 5, 6. X is 1, yeah. That's true. R of 0 is less than R of 1, which is not true. So this exits immediately. You get this length 0, 0, I is equal to 1, right? Because x start off at 1. Identify and process a decreasing sequence. So that's this one, x is less than n minus 1, true. This is greater, so this is true when x is 1, right? 6 is greater than 5, increment x. And you go all the way across, right? The length is then x minus I, you increment ret by the length. Oh, and you're supposed to update I to x. I forgot about that. That's important. That's probably why that's happening. Okay, I is 1, and we exit. So we get 16, we expect 21. So what's interesting is we start off at n so we start with 1 candy each. We get its sequence 0, 1, 2, 3, 4, 5. Length is 6. We decrement the length by 1, so we get 5, and we take 5 times 6 divided by 2 is 15. So you would add 15 to 6, so we should get 21. That would be processing this decreasing sequence. Now, the question is, where does x end up being? So length should actually, so x actually ends up, this fails at some point. Now, when x is less than n minus 1, so x has to be less than or equal to this value. So n minus 1 is this index. It's got to be less than n minus 1. And then what's going to happen is we compare these two, x increments. So x is starts off at 1, goes to 2, 3, 4, 2, 3, 4. That's the index. This will succeed. X will be at 5. This will fail. 5 minus, now I is 1. So actually what's interesting about that is it's actually I minus 1. So that's curious. You actually have to add another one there because they're moving the length back 1. So you would get 6. So I at this point is 5. And what's also interesting is x is an index. Excuse me, x is 5. X is an index, not the length. So you would take the difference between this index and also add 1 again as well. So I think you actually add 2, which is kind of curious. But it looks something like this. It's x minus I minus 1, which means a plus 1, and then this is an index. These are indices, so you add another 1. Excuse me, which I think might be too much, actually, if we do it this way. Yeah, no, it's too much. That was too far. Why all these things? 5, 1 to 5, and then you subtract 1, minus 1, and the reason you subtract 1 is because our summation is going to be the length minus 1. So plus 1 minus 1. That's really interesting. How that works. Yeah, that's quite the quote unquote off by 1 error going on there. And by the way, if we had a decreasing sequence, x would end up pointing to the end of that sequence. Yeah, and then it would start the next sequence. Right, so that's actually correct. Same thing on the other side. So it's actually x minus I plus 1. These should be the smeared calculations, by the way. So how you actually got the x minus I plus 1, there's like 3 or 4 different things to factor in there. Maybe that's why this is a hard problem. Let's see. So, okay. So now you have the same thing if you're going left to right, but the problem is that this length is, oh, I see the length. Oh, that's awkward. Okay, I see the problem. So the length should be, it's going to be like this: x minus I minus 1 is the length. Right, that's the correct length. And then when we add I minus 1 goes to 0. X minus plus 1 is the correct length, right? And then we say we actually subtract 1 here, decrement the length for the calculation. So if length is greater than 0. Now what could happen is the length could be 0, and what's interesting is, so if x is equal to I minus I minus 1, so that's really interesting. Assuming there is actually this is kind of gets back to the overlap, I think, a little bit. So, because I is ahead a bit, so it's x starts off with sort of a head slightly. It might be better to do things the other way around. It might be better to do I starts off at 0, and I is less than n minus 1. Yeah. Maybe that's what I'm doing wrong. So I starts off at 0. I don't think we need this anymore. I think we figured out what the issue is. So x starts off at the same index, and we do x and x plus 1. That's maybe more correct way of doing this, right? So yeah, that's better. That's a lot better, I think. Oh yeah, that's actually was really confusing, because actually in that other case, I would have to go all the way to the end. So r of x is less than r of x plus 1, n minus 1, x equals I, starts off at 0, goes over to 5, right? So 0 to 5, 5 minus 0 plus 1 is 5, or, oh no, excuse me, it would go to 4. But it would be true, then it would go to 5, and then at 5, it's too far. So then it would go back to, so that's the correct spot. Okay, so now we could do x minus I plus 1 for the correct length. What's interesting about that, though, is if they're equal to, x and I are equal to each other, that means the length of 1. Which is really tricky because we're adding 1 here each time. So what we want to do is only add the lengths that are at least, only consider lengths that are at least 2. I think so. I think that's part of the issue. Yeah. Now what's interesting is, yeah, because we're gonna end up considering like here. So we should only do if length is greater than 2, is greater than or equal to 2. You can see why this is a hard problem. This definitely is challenging. Okay, how are we doing on time? Almost an hour. All right. I mean, an hour is not too bad for a problem that's kind of unfamiliar to me. So once we've gotten past our sequence, we'll set I to x, wherever that ends up being. And yeah, it should be the last traverse to the end of the sequence, to the last element. Last element of the sequence. Monotonically decreasing sequence, set x equal to I, perform almost the same thing. R greater than x plus 1, increment x, r minus I plus 1, if length is greater than 2. Okay. And then update I to x, the last element, and then say if we're not changing at all, then I is less than n minus 1, and we don't process the last element. Somewhat ignore it. Excuse me. So r of I is equal to r. It's not that we ignore it, and we process that last element in each of these internal pieces. Excuse me. So non-changing sequence will be ignored. So if I is less than n minus 1 and this value and the next value are equal, then we just scrub forward. Think that handles the case that we had that was wrong here? No. So it's still wrong. Oh yeah, and now we have to subtract 1 from the length as well. Because we've already calculated 1 layer to start with. Yeah, so I did an extra addition. Okay, let's go back to our test cases. So I think this will give us the right answer. There might be a more concise way of doing this, but I think if this works, that's okay. 50 minutes. Wrong answer on one of them. All right. After all of that, something's wrong. Whoa, a lot of them are wrong. Okay, let's grab 1/3 from the bottom. Okay. 1, 2, 3. Is the whole answer wrong? I mean, the whole idea? That would be upsetting. Okay, we got 14, could have done 13. 6, 5 gives us a sequence of 2, 1. 6, 5, 4, 3, 2, 1. 6, 5, 4, 2 gives us 4, 3, 2, 1. Yeah, 4, 3, 2, 1. And then 3 gives us 1, 2. And then 3, 1 gives us 2, 1. Oh, I think I see what the problem is. So, maybe better to actually not do the calculation with the initial candy, the initial value. And my thinking is, we can save on our length, right? We can add the full amount, but also I guess what's interesting is I think actually the sequence that we put at the end, like the sequence that we attach, that depends on what our ending value is, right? So if we have a monotonically increasing sequence and then a monotonically decreasing sequence, we only need to guarantee that the ending point, that value stays fixed, or the ending point from the starting point, that value is fixed, but the ending point of our sequence, or in other words, the monotonically decreasing sequence after a monotonically increasing sequence, there could be kind of a cliff there where we might go like 1 all the way up to 10, and then there's only 3 smaller values to the right, or 2 smaller values to the right. So then we could take excuse me. We could take the sequence going all the way down to 1. So we can go 2, 1 for those last 2 values, and then we just have to keep the first of that sequence at 10. So we go 10 drops all the way down to 2 and 1. So we don't necessarily need to add the entire sequence. I guess that's maybe the first thing. So maybe we should write this in such a way that write this in such a way where we don't factor in the first element. We can add all the candies, and we just don't factor in the first element of each of these sequences. The first element should be set by the previous routine. Yeah. And we could just set the first value as needed. Yeah. That's a simpler way of doing this. I think that works correctly too. There's probably like a better way to do this, but there's like a little bit of overlap between the sequences, so it gets kind of confusing. But you can say something like the following. So we're going to set this to 0 initially. We're not going to decrement the length. We are actually going to decrement the length still. And I'll explain. We just don't factor the first element. Yeah, that's the key. If we're going increasing and then decreasing, there's another issue here too, where you have increasing sequence and then a very large decreasing sequence. You may have to jump. So maybe we do need to manipulate this first value. Oh, it's so confusing. Excuse me. Oh, let's see what is considered a hard problem. All right, we've used quite a bit of time now. I'm gonna stop checking the time. We're definitely at a point of like, okay, it's been a while. It's been a while. So I think what we need to do here is the beginning of the sequence. When we're writing the sequence, we need to check to see what value that needs to be, that number. Yeah, because you could have a very large increasing sequence and a small decreasing sequence, or you could have a very very small increasing sequence and a very large decreasing sequence. And in both cases, the decreasing sequence need to be at least large enough at that point for the decreasing sequence, and if you have a very large increasing sequence and a small decreasing sequence, you just need to be big enough for the decreasing sequence. So you need to keep track of what the value is expected at that point. So we have like a previous value, I guess, or a starting point. We could set that each time. So you have some previous value. I'm not sure what it's going to be initially. I guess we could say it's 1 or 0 or something. I don't know. Monotonically increasing sequence. Traverse last element sequence. Update. First value sequence appropriately. So if the length is greater than or equal to 2, so if this is monotonically increasing, excuse me, monotonically increasing, actually what I've only been looking at is decreasing, but if it's increasing, it's the other way around. So if the previous value is really high, and now you're increasing, would you lower that value? To have some decreasing sequence. It decreases all the way down to 1, by the way, the decreasing sequences. So increasing sequence should go back up to up. Even if it's a very large decreasing sequence, it's still going to end up down at 1. So increasing sequences don't really have this problem. It's only when increasing to decreasing. Decreasing to increasing is really not an issue, pretty much ever, I would say. Only issue you're going to have is you set all these values at this point. You would have already added that first element. Yeah, we decrement the length before we do this though, so that's fine. So we won't add that. We won't add the first value. Is that good though? That's so awkward. I think actually we do want to start this off at n. There's a lot going on here, man. There's a lot to explain. I think you don't actually touch the previous value at all. Monotonically increasing sequences, you don't really care. Excuse me. Yeah, because you could make your decreasing sequence as small as possible. Pretty much always. It's only when you're going from increasing to decreasing where things really make a difference. Actually, also for non-changing sequences, I think you drop the amount down to 1. By the way, you assume they're all at 1. Excuse me. So I think previous would go to 1. But yeah, actually in this case, you just set previous. You don't really touch this. So the next previous is going to be the value of the last sequence, which is something we really don't need to think about then. Starting point is going to be oh yeah, actually we do want to do it that way. So that's going to be something like the following. So based on the length, so the length is 6, you're going 1 to 6. So it's going to be exactly the length. That's the value of the previous value. Now over here, we know the previous value. So we're going to go ahead and now we can say if we have a decreasing sequence now, we have two possibilities. The decreasing sequence could be a lot smaller than the starting point of the increasing sequence, in which case so what's interesting here is that, yeah, we still, well, on the increasing side, we're not processing the first element. On the decreasing side, we are processing the first element. We're not processing the last element. When we decrement the length here, it's actually the last element we're not processing. So what's interesting there is, first off, we're adding I'm sorry, is that true? Because there's a couple things going on here too, where we added 1 to everything. Wondering if we should be doing that. I don't think so, actually. I think it's better if we just don't. I think it's simpler if we get rid of this. And we say, just don't change the length. Just leave that. And that way, yeah, we add our monotonically increasing sequence, and now we want to take a look at our decreasing sequence. Now the deal is the decreasing sequence, we're going to add that increasing value. We're going to add that again. So we can subtract that by decrementing the length. So yeah, don't process the first element of the sequence. Don't process the first element of the sequence by decrementing the length. So we're only going to do the ones to the right. And part of the issue is the first element could be a lot larger. Now, if the first element's a lot larger, then what we just wrote will be fine. It'll handle that case. If the first element's too small, though, then we need to update that element and take the difference between the size and what it currently is, and add that. So it could be, it can't be 0. There's another issue here. The things that are zeros need to add a 1 to that too. So could you have a 0? I don't think so. Well, yeah, I mean, let's suppose for a moment we don't have zeros. Interesting. I'm actually not sure. Do we assume that all of them are at least a 1? Maybe that's the wrong assumption. Oh, dude, there's so many. I see why this is a hard problem. I get it. I see it. This is really a lot going on here. A lot of details. Previous is always at least a 1. So Some cases will be a 2. I want to say here if they're equal to each other, we could go down to a 1 and set previous to a 1. And then yeah, so previous will be always at back to a 1 after a decreasing sequence, by the way. Not sure if that really matters, but might matter. Yeah, the main issue is that the previous value could be too small. That's the main problem. If the previous value is too small, and we assume we already added the previous value, so we would subtract the previous value and previous value is going to be subtract the previous value and add the new value that you need, which is going to be the length. Yeah. Don't further process twice. Don't process the first element of the sequence again. A second time. And now the issue you see is non-changing sequences will be ignored. So if R of I is equal to handle non-changing sequences. So here, if these are equal to each other, then we could set R of I plus 1 equal to 1. Simulate setting. To 1. Simulate setting that to 1, so you'd have ret plus equals 1. So this is, yeah. Something like this. Let's see if this compiles. Start with that. There are some issues here. How are we doing on time? Okay, we're like really taking a lot of time, but this is all right. This seems to be working for the most part now. Now you run into issues with certain test cases, like if you have 0 or 0, 1 or 100. I think these don't work. Don't work properly. Yeah. So let's see which ones. I think it's the first and the last. I think the middle one will be okay, but the first and last won't work. And I think it's the only real issue you have. If you have like all zeros, for instance, or you might have an issue with that too. I didn't really think about like handling those cases properly. Might be some issues with those too. 2 expected 2. So we got 1. Yeah, because we set this value to a 1. We don't, the initial value we don't touch. And then 5 zeros. Actually, we could just set ret to 1 and simulate adding yeah, previous 1 and ret 1 is just always the case. See, the problem with that is this won't work properly for sequences that So this doesn't set the first value. The first value could be a 0. Yeah. So the problem we have here is that this handles the full sequence. This handles the full sequence. This assumes that you've set the first, that you already processed the first element of this sequence. This does not assume that you handled the first element of the sequence, and this also assumes you handled. So these two assume that you handled the first element of the sequence. This one doesn't. So I think we need to ensure that we do handle the first element of the sequence. Does this minus previous? Yeah. So we should do ret1 previous one for decreasing sequences here. Actually, does this break if we do ret1 previous one for it was like the fourth one from the bottom. 1, 2, 3, 4, something like this. Hold on, I forgot which one now. It's the one that we were working on. 18, 17. Yeah, we end up with one more than we should. I think the reason for that is because this should not assume. Oh no, yeah. Monotonically increasing, we just subtract 1. Process the sequence, subtract 1, and move the first element of the sequence. Oh, yeah. Monotonically increasing, it's always going to be, the candy's always going to have to start off at 1. I think we can guarantee that. Okay. Oh, they're all right now. Yeah. There you go. Okay. I think that's probably it for everything. Really interesting question. So this should be linear. Oh, nope. If this works, big caveat there, this would be linear time and no extra memory, which is quite efficient. Oh, there are a few test cases that fail. Okay. Quite a number of test cases that fail. Oh, here we go. 11. Which one is that? Can I identify that? There are a few 11s. There's like 12, 13 with a few 11s and a 3. 3 11s, so it's the second from 13. Second down from 13. That one. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Number 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. This one. Let's go to the beginning here. Check if that's the one that's failing before we delete everything here. All right, I give it. This is a challenging problem, hard problem. One of the harder ones. Okay. Oh no, that one's fine. I missed. It's one of these 11s here. Let's go above and below. Should be somewhere there. From 15. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Alright. Yeah, there's so many test cases, it's hard to figure out which one's failing. Even if they tell us which one's failing. Okay. So it's the second one here from the top. Alright. This one. So 6, 5, 2, 3, 4, 1. This one fails. And why is that? 6, 5, 2, 3, 4, 1. So process 6, we have 1. We say 6 down to 5. We would potentially remove, so we would subtract the previous, add the length, which is 2. Add 2, decrement the length, so we don't process 2. This goes to 1. Then this is 1 times, so this adds 1. Previous is 1. So we add, so we'd start with 1. We go to 3, right? Subtract 1, add 2, and then add 1. Because add 3, so we have 2, 1 now. Excuse me. This actually would go 3 down. So this goes 3, 2, 1. So there should be. We'll process ret. We'll just debug. So we go 3, 2, 1. So we go red is 1, goes to 6, and then we have an increasing sequence. So now increasing sequence goes 1, 2, 3. We would say the length is 3. Um, 1, 2, 3. Length is 3. We would subtract 1 to not process the first one, but we would add 3 times 4 divided by 2, which is 6. Add 6, subtract 1, so we add 5. So we add 5 here. So we go 3, 2, 1, 2, 3. And then here we just have a 1 with this decreasing sequence. We would, another decreasing sequence, length minus previous. So previous is 3. We would subtract 3, add the length, which is 1, decrement the length, goes down to 0, and we'd be done. Now, what's weird about this is this should give us the right answer. I think this part might be the issue. I think I need to actually make a. We only need to do that if the decreasing sequence is. If the decreasing sequence. Oh, I think it's too small. Yeah. Okay. Yeah, the problem is, so we go 6 plus 5 puts you at 11. So actually, yeah, we subtract the previous and add the length. That's if the length is greater than the previous. So really it's going to be, yeah. That's only if the length is greater than the previous. Otherwise, you just don't bother. Okay. Yeah, I was I spoke that before, but I forgot to add that here. This is like not a very clean algorithm here, as far as like, oh boy, how many of these do we have? Hundreds of test cases. That's about right though. It's kind of what you ought to do for something like this. Oops. This is really a lot of work. Hour and a half now. Hey, all right, I think we got it. If it passes all those test cases, it's very likely that it's correct. Now, what's interesting is we can make things even more complicated. So, I can add some duplicates here. All right, so let's get rid of all this. Keep the ones at the top, that's fine. So it's probably correct at this point, but the problem is that we didn't really, there's some things we still didn't test, some cases we still didn't test. All right. Okay, ready? We want when there are duplicates. So we're going to go 2, 2, and then 5, 5, and then we'll do like 1. Something like this. Now this, there's a lot of permutations here. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 factorial, which is a lot. Yeah, factorial. That's 40 million test cases. Okay. Okay, we don't need 40 million test cases. That may be too many. So we can get rid of some of these. Let's get rid of like 3 altogether. Let's get rid of like 6 altogether. We can maybe get rid of 1, 2. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, now I'm at 9 factorial. Still a lot. 360,000. I don't think we need 360,000 test cases. A lot of these are going to be the same too, actually. Let's do this. Get rid of 5. Let's try that. Yeah. A lot of these are actually going to be duplicates. I didn't really think about how to do that more efficiently to get like more interesting test cases. Okay, so handles, yeah, a lot of different variations we have. Yeah, I forgot, there's a way, I think they would be combinations. It's a way to not have duplicates. I think it's permutations without replacement. No. It's like a multinomial kind of a expression, like counting how many permutations there would be with duplicates is not a complicated thing, but generating all of those. I actually don't know. How do you generate permutations with duplicates? I think normally I would just generate all the permutations and then put them in a set instead of an unordered set instead of a excuse me, instead of just a list. But there's probably a way to do that that's better. It doesn't do all that extra work. I don't know how though. You can use. I actually do know. You would use a frequency map. So I know how to program that. You just each element, when you place it, you have a frequency map that you use to place the elements, and you just have to make sure that you have placed one of each, like basically decremented the frequency map all the way down to 0 for everything. That's all you have to do to get all the permutations with duplicates. I don't know. Python definitely has a routine for that. What can we do? Permutation with duplicates. We have the documentation here. Excuse me. Permutations, combinations with repeated elements, with replacement. So what is the difference between permutations of A, B, C, and D and the combinations of A, B, C, and D? Well, combinations are slightly different because they don't have, they have sorted order, more or less. So it's like a set of elements. So yeah, it's really confusing looking at it in this form because combinations give you a set of those elements. So A and B and B and A. So B and A and A and B exist in permutations, but they don't exist in combinations. But that's not what permutations with duplicates looks like. So yeah, so you wouldn't do combinations. If you wanted those repeated elements. The product's repeated. Oh, that's interesting. That's basically a Cartesian product. And then you can repeat. I don't know if the repetition happens on all of the values. That would be kind of a lot. Yeah, that's interesting. I don't really have unique permutations. I don't really have a clear. Anyway, pretty interesting. I like the iter-tools library for Python. But anyway, I think we're done, by the way. I think we got it. It's been an hour and a half, but yeah, that was not the cleanest way. I mean, it's pretty involved. I mean, I'm fairly confident. All right, we got the other test case. We got with duplicates test case. Yeah, there we go. Okay, we're in good shape. We got it. I was thinking like it's pretty clear indication that we got it. Now, yeah, this doesn't use very much memory at all. This is constant extra memory and linear time. It's actually one pass, which is interesting. There we go, almost 100%. Can we get 100%? I mean, probably if we keep running this, we get 100%. That's pretty good. That's pretty good. So yeah, thank you for watching. This was kind of brutal though. This was like, really took me a long time. I just want to keep running it until you get 100%, but I don't think so. I think we'll get that. You'd have to just keep trying until you get there. I guess you could do this a little bit faster somehow, to get that like extra 4 milliseconds, but I wouldn't know how. It's probably about as fast and as little memory as you can get without getting kind of splitting hairs. My question is like, is there a way to code this better? Possibly, maybe. Maybe there's a way to do this that doesn't have all these branches. Like I have these 2 if statements in here. Maybe there's that. There's got to be a way to do this that's a lot cleaner. But the basic idea, all right, I think we'll take our 12 milliseconds and it'll be done. If we got 8 milliseconds, it looks like somebody got 8 milliseconds somehow. All right, we'll end it there. So I think really interesting question. Also click the wrong button there. Really interesting question. I think the issue is really interesting question. I think the issue is that was a question of processing monotonically increasing and monotonically decreasing sequences and non-decreasing sequences. So or non-changing sequences. So there's increasing, decreasing, and non-changing. So there's 3 cases, and those sequences connect to each other. So you have to handle, like if you make the assumption that the first element is processed already, and then each of those sequences will then don't have to assume that the first element's processed. Then you can chain them nicely, each of those cases, in a loop, which is what we did. And we also we had some logic, right? Each of them had some logic. We had some cases where you had to consider when you actually connect those chains to each other. There's different scenarios to ponder. There's quite a few. And then also there is an issue of like how do you actually once you've actually identified an increasing or decreasing sequence, like how do you actually update your result value with how do you process that? Right, we did a little bit of maths in there to there's a iteration kind of what do you call it? A little bit of summation logic, right? So if you're going to perform a summation from I equals 1 to n of I, right there, that's like a common. You'll see that a lot, or frequently enough. I see that I've used that formula a few times. So here it's useful. So we can just count the length and then use that, compute the sum there. Excuse me. Yeah, use 1 multiplication based on the length. Wondering if we can. Wondering if there's a better way to do that. There might be a way we could update things where I don't know. I split the logic into the loop and the if statement afterwards. However, the summation logic we could perform. Well, you want to do it that way, so it's easier that way. The logic is easier that way because then you can say things like, oh, we're only going to process part of the sequence, and oh, we're only going to do something if there is a sequence to work on, something like that. It's a little bit easier to kind of like split things up if you do it that way. I think I prefer that. I think I'll just leave it that way. I think it's simpler. The other way would be like within the for loops themselves, do the sort of the logic, the adding and subtracting and things like that. But it's a little bit harder to like consider quote unquote removing the head of the sequence and only processing the rest of the sequence. Although you could have like a count variable that increments, that gives you the length of the sequence, and then you could process later. You might be able to optimize slightly, very slightly. I think you can optimize instead of performing some multiplications at the end. You can just do strictly additions. I think there is a way to optimize that approach, but I'm not going to get into that now. I'm just gonna leave it where it is. So yeah, thank you for watching. I'm going to go ahead and take a look at the next problem. Well, I'll take a break for a while. That was a bit of a doozy. That was a lot. Handling sequences is like a common thing, you know, increasing, decreasing sequences. You'll see that a lot in these problems, but I guess not having like a tremendous amount of experience with that, when you see it, it's just kind of like, you know, it's a lot, sort of a lot at once. This question was not really so much about like other kind of data structure related things. This really was like a how familiar are you dealing with kind of unusual processing kind of a question. I've seen this question before too, or similar questions before. This is a very interesting question. But yeah, linear time solution is fine, works. You can handle increasing sequences, and there's just a lot of like logic around that. So pretty interesting question. Probably really hard if you saw it in an interview. I guess that's why it's considered hard. Like it took me over an hour and a half to work through all that. That was pretty involved. Even if I knew the answer out the gate, I think it would still take me like 10, 20, 30 minutes just to code it, because it's, you know, well, it's not that, I think that's just part of the problem, is that like you'd have to be really familiar with like coding strange cases dealing with increasing sequences, and manipulating those like sequences that connect to each other. You'd have to be really familiar with that in order to like code this very quickly. I don't know if I'd be able to code this that fast, even after having done it before. Like I'd probably need to have some idea of like what I'm coding first, and then I'd have to think about like better ways to approach the problems. That way programming it's a little bit easier, something like that. But yeah, I think the basic idea that I had was like breaking into three cases, and then each case doesn't process the first element, and only updates necessarily the first element, assumes the first element of that sequence, you know, the last element of the previous sequence is already added. I think that was the way to go. That's pretty logical and simple and easy, and yeah, that's like relatively easy to debug too. And you break into three cases: non-changing sequence, increasing sequence, decreasing sequence, and then go from there. But yeah, thank you again for watching. Talk to you soon. Have a good rest of your day. And yeah, I'm gonna take a break. I don't know what I'm gonna do next. Just take a break and kind of just let all that sink in. We just went over. So yeah, take care.